Welcome to Lesson 4B, Particle Explosions. This time we'll deal with particle explosions. We'll discuss something similar to the LEL, which is the LFL for particles, and autoignition temperature. And I'll do a quick example. We've discussed vapors or gases, and we had the lower explosion limit, upper explosion limit. Here we're going to talk about dust, dusty air. You have some kind of a container or room, and you have a whole bunch of tiny particles in it. These are called aerosols, by the way, when they're very small and they're kind of hanging in the air. They slowly fall down, but if the room has some currents, they kind of just move around, hang in the air for a long time. So aerosols, powders, and this can come from like pulverizing coal, for example, so coal dust. And if you have a high enough concentration, and just like with the gases, if there's a spark, then you can get an explosion. We'll define something here that we call LFL. Really the same kind of idea as LEL, but this is for particles or dusty air. It's called the lean, not lower, but lean flammability limit, which is the minimum concentration at which it can explode if there's a spark. In addition, there's something called autoignition temperature. The lean flammability limit is typically in gram per cubic meters, so that's a mass concentration. But autoignition temperature is a temperature at which it will explode even without a spark. So that's even more dangerous because it can explode even without a spark. So these are the two main ideas in this case. Now it's a little more complicated with particles. We're going to spend quite some time on particles later on in the course. But unlike gases that depend only on the concentration, the particle size is also a parameter. Large particles are less likely to explode. When I teach, or even when I just think about things, I like to look at extremes to help me understand what's going on. So let's take, for example, 1 kilogram of coal. Here's two identical containers with air and coal. The first case, we take a chunk of coal that's 1 kilogram, one particle, and you try to suspend it in air. Well, obviously it's going to fall to the floor and this will not explode. There's no way this can explode. I don't care how many sparks you have. In fact, it'd be hard to even light it. You'd have to put a flame close to it for a long time to even get that to light. On the other hand, let's take the same 1 kilogram of coal and let's pulverize it. By the way, this is 1 cubic meter, these containers. So you have a cubic meter. And now we're going to pulverize this coal into billions of 20 micron particles. Still adds up to 1 kilogram. So we got all this dusty coal here. It depends on temperature too, but at room conditions that can explode if there's a spark. Both of these have a mass concentration of 1 kilogram per cubic meter. But these are vastly different animals here. The one on the right is the one we're concerned with that could possibly explode when you have dusty air. This LFL will, of course, depend on the particle size, and so will autoignition temperature depend on that size. Another comment is that, as with vapors, the LFL is typically much, much greater than the PEL, or the threshold limit value if you use the ACGIH values. So I looked one of those up. The TLV for coal dust is 2 milligram per cubic meter. Coal miners are very interested in this value. So ACGIH says they shouldn't be breathing air that has more than 2 milligrams of coal dust per cubic meter in order to avoid black lung and other lung problems, emphysema, etc. But the LFL for coal is typically around 100 gram per cubic meter. This is a factor of 50,000 times greater. So this is true, just like for gases, LEL was typically much bigger than PEL. So the bottom line is, if it's dusty enough to explode, you really should not be breathing it. You'll be in very bad shape. And if you're able to breathe it, it's most likely not explosive. Here's some examples. This can happen not just with something that you think of as flammable like coal. This can happen even with grain. This is an explosion in a grain silo. You have some kind of a silo with grain, and if that gets stirred up, you have all these particles. They can burn, and in fact, if the concentration is high enough, it can explode. So here's an example of that. This is wood dust, which you do think of wood dust being explosive. So there was another case where something exploded, exactly what we were talking about. There's a very recent example from an explosion in Beirut. I'm recording this on August 28th. This was just a couple weeks ago. Probably all heard of that huge explosion in Beirut, Lebanon. That's not quite the same because this was ammonium nitrate that's used for fertilizer in Beirut, Lebanon. It's kind of a white crystalline particulate that was stored. And I don't know the details if these particles were in a dusty environment or they were just sitting there and it got too hot, but they eventually did explode. They were worried about it for many years, but nobody did anything about it, so it was quite a tragedy. Here's an example. We're going to look at coal dust. The air in a coal plant contains suspended Pittsburgh bituminous coal dust at standard ambient temperature and pressure. Pittsburgh bituminous coal is a hard coal. Back in the industrial age, this was very important. Not so much now, but for the steel industry and everything. Density is given, and we're going to talk about 20 micron particles. And we want to predict the mass concentration and the number concentration, number of particles per cubic meter, at which this dusty air is likely to explode if there's a spark. And so how do we find these LFLs? Well, we give some examples in the textbook, and you could look these up on the internet for other kinds of materials. For Pittsburgh bituminous coal dust, we happen to have a figure 319 here, which shows the LFL in gram per cubic meter versus particle diameter, dp, in microns. So we're talking about 20 micron particles.
The plot agrees with your thought experiment. LFL goes up as dp goes up.
That's right, BJ. This has 3 different oxygen concentrations, 50%, 15%. These would be in situations that are controlled types of burning. But in our case, we're talking about room air, standard air. So we want this middle curve, 21% oxygen. So we just go up at 20 microns to that middle curve and it's straight across. And so I'm going to call that to 2 digits, 130 gram per cubic meter. We want to know the mass concentration and the number concentration. Well, the mass concentration is simple, and I'll drop the J subscript here. So C is the mass concentration at which it will explode if there's a spark. Well, that's equal to the LFL since LFL is in units of mass concentration. So the answer is C is 130 gram per cubic meter. So that one's trivial. Now we have to convert to C number. So I'm going to call C number, and we haven't defined this yet, but for particles, we'll talk about this more later, is the mass concentration divided by the mass of one particle.
May I ask, sir, how did you come up with this equation?
I basically figured this out just by units, because you can think about this as particles per cubic meter equal mass per cubic meter, that's C, and then mass per particle, and that's in the denominator. So we invert that, and you see that the grams would cancel out, and you end up with particles per cubic meter, which is what we want. So all we need to do is calculate the mass of a particle, where, and then what's the mass of a particle? Well, we'll assume spherical particles. It says diameter, so we assume that they're spheres, or equivalent spheres. We'll talk about equivalent diameters later. And so M particle, the mass per particle is the density of the particle times its volume. And the volume of a sphere, make sure you remember that, is pi dp cubed over 6. And so when we combine these together, we can calculate C number is equal to 6C mass concentration. So number concentration is 6 times mass concentration over pi, rho p, particle diameter, dp cubed. And that's our answer in variables. The rest of it is just numbers and conversions. Be careful with these kind of problems where you watch your units, because we mix up microns and kilograms and grams or milligrams, and so you get some factors of 1,000. So let's just plug in the numbers. C was 130 gram per cubic meter. Pi, my density was 1,200 kilogram per cubic meter. And then the diameter is 20 microns, so that's 20 times 10 to the negative 6th meters cubed. I got grams and kilograms, so I want to do a unity conversion. 1 kilogram is 1,000 grams. And if you look at my units, the grams cancel, the kilograms cancel, one of these meter cubes cancel, and you end up with your answer as 2.59 times 10 to the 10th particles per cubic meter. This is only good to 2 digits, so I would say that C number for my final answer is 2.6 times 10 to the 10th particles per cubic meter. Since that's such a huge number, What's actually more typical with number concentrations is to change this to millions of particles per cubic meter. So we would divide by 1,000,000, and so this would be C number. This is kind of the preferred answer if you're writing this up in a paper or something, is 26,000 million particles per cubic meter. So that would be my final answer to 2 significant digits.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.